Alright, we're continuing on in 12.1 with lecture B. So this is 12.1b, and a series is what they're going to look at here. It's the sum of a sequence. It's adding up a bunch of terms. They can be infinite without end. That doesn't necessarily mean that their sum would be infinite. Sometimes things limit out and we're able to converge to an answer, and that type of wording will be used in there. They can be finite, where we're adding up just the first 6 terms of something, right? The sum of the first 6 whole numbers. 1 plus 2 plus 3 plus 4 plus 5 plus 6. This would be the sequence an equals n. The sum of the first 5 even whole numbers. So this would be this sequence an is equal to n, right? And so we would be adding that up from 1 to 5. Sum of the first 4 powers of 2 are there, and we get 30, right? So sequences are just sums. So we have this summation notation. Hopefully you've seen it before. This Greek letter sigma means to add. And so it's not a sequence anymore. It's what we call a series, or an addition of a sequence. There are 3 parts to the notation. There is the symbol itself that says to add, and then they're telling you where to go to and from, a lower index and an upper index. So for example, if we look at example 1, we're supposed to add up all the 2k's from k ranging from 1 to 5. And k is an integer, right? K is just like our old n. They're going to use k here, so it looks a little bit different than a sequence. But essentially what they're asking us to do is start with 1, then go to 2, then go to 3, then go to 4, and then go to 5. And I'm putting pluses in between them, not commas, because of the summation notation. So this is 2, 4, 6, 8, 10. And they're asking us to add those together, just those 5 terms, right? And so the numbers in the parentheses are the indexed values, right? They're the first term in this sequence. But then I got to add it to the second term in the sequence. So if we look at this, this is 10, 20, 30. So we get a total of 30 there. And then what's happening here? Well, we got to add, starting with k equals 3. So now we got to take 5 times 3 plus 1, plus 5 times 4 plus 1, plus 5 times 5 plus 1, plus 5 times 6 plus 1, plus 5 times 7 plus 1. So you can see that this would be a problem if we had a whole bunch of, like if it went from 3 to 70. That would not be fun. There's got to be a better way, and there is. We'll see what they present to us. But essentially here, you would say, hey, this is 15 plus 1, that's 16. This is 20 plus 1, that's 21. This is 25 plus 1, that's 26. This is 30 plus 1, that's 31. And this is 35, 36, right? And we get a nice 36 out of it. And you would add all those up and be done. That would be your series, right? It totals up to be 30. Okay. And then he's going over the notation again as well. Let's see what we need to do. Okay, so he's going to recreate some of the stuff we did earlier. Sum of the 2k from 1 to 5. You plug in k equals 1, 2, 3, 4, and 5, and you get the 2, 4, 6, 8, 10 like we did, and those total 30. Now if we go from 3 to 7, we're adding 6, 8, 10, 12, and 14, and those happen to add up to be 50. So what is the relationship between k and n? The variable which represents the term in a series, the variable n represents the term in the series that you are at. If n equals 1, you're referring to the first term. If n equals 2, you're referring to the second term, and so on. K is the value you're plugging in to get to that term. Okay, so they just use a different letter when they do the series. But again, we're just going to plug in 1, 2, 3, 4, 5, so forth and so on. And I'm not sure why these are looking the way they are. because he has 1 to 5. So this should be a 1, this should be a 2, this should be a 3, this should be a 4, this should be a 5. Um, if k starts at 3, then you get 3, 4, 5, 6, 7, 8. Yep. And so they're saying that even though k is 3, it's still the first term that you're looking at. So a1 is always the first term, and it may not always be found by plugging k equals 1 in, right? Formulas for this series. So some of these formulas you'll know. I mean, you should know that if you have 8 plus 8 plus 8 plus 8, that the fastest way to do that is say, well, that's 4 eighths, or 4 times 8, right? I got 8 4 times. That's where the times name came from. And so you would take c and multiply it to itself n times, right? That's all that's happening, where c is an element of the reals. So if you wanted to sum from 1 to 12 of 6, well, no problem. That's just 72. It's 6 being added up 12 times, first time, second time, all the way up to the 12th time. And 6 times 12 is 72. If you're going to take negative 4 and multiply it by itself 20 times, you're going to get negative 80. Sorry, if you add it to itself 20 times, you're going to get negative 80. And then this is an interesting one, right? He doesn't go through a proof at all. There are proofs that are laid out. The sum of the first k terms are n, or sorry, the sum of the first n terms are n times n plus 1 over 2. So if you really wanted to quickly add something like 1 plus 2 plus 3 plus dot 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 plus 100, what this is saying is you take 100 times 101 and divide by 2. 2 goes into 150 times, and then what would that be? 5050 would be the sum of the first 100 numbers, right? You would take n would definitely be 100 in my blue case, n plus 1 is 101 divided by 2, and it works great. You get a nice 50-50 out of that. If we added the first 20 numbers, it's 20 times 21 divided by 2. That goes in half, and you can see where the 210 comes from. 1 to 40, 40 times 41 divided by 2, so forth and so on. There's others that can be there. Okay, k squared, a little bit more complicated. N times n plus 1 times 2n plus 1 all divided by 6. Pretty easily shown using the previous result. And again, most books would show you that as well, where that came from, but that is the formula. You'll want to have these formulas with you when you come to take the exam. Don't feel bad about writing them down. They'll be on the outside covers of your calculus textbook as well. They're that important, especially in that second series. And so here we recognize that n is 6, and so we're just plugging in 6 times 6 plus 1 times 2 times 6 plus 1. And you can see where they're getting all those numbers. So, and then here, first 11 terms, 11 times 12 times 23, right? 11 doubled is 22, plus 1 is 23, and we get a nice 506. And then the sum of the cubes looks like that as well, and that's usually where we'll stop. Let's see. Yep, that's where we stop. And then if we needed to, we can bring out constants because they're just there, right? So all this is saying is, hey, if the same number is there every time, you can just bring it out front and multiply. So example 1, 3 times k, they're saying, hey, just bring out the 3, and then realize you got the sum k equals 1 to 10 of k. Well, that means you got 10 terms in there, so that's 3 times the 10th term, 11th, all divided by 2. So n times n plus 1 divided by 2. And so that's a 5. It's a 55 times 3, and that's going to give us the 165 that's over there. And then you could split the sum over the polynomial. So if you had something like this sum of 1 to 5 of k plus 4, you could split it up where you're using the formula here and then the natural consequence of the fact that it's the same 4 being added every time. And so you get 5 terms, so 5 times 6 divided by 2 plus 4 times 5 is equal to 35. Pretty cool in that regard. And then same thing with differences. It wouldn't make any difference if it's a difference as well. So here we have the sum of 1 to 6 of k squared minus k. We don't have to get overwhelmed. We don't have to look for a new formula. We're just going to distribute out the sum to each one of those blocks. We have a formula for this. We have a formula for that. And we are going to just use those formulas. So here's the formulas copied down with the numbers in there, 6, 7, and 13 with the 6, 6, 7, and 2 in there, and we get 91 plus 21 for 112. You can break the interval into two pieces if you need to, if you needed to go over a certain amount. So k equals 1 to 8 is k equals 1 to 5 and 6 to 7. That doesn't really show you its power, but it needs to be stated. Okay, so yeah, why do we even state this rule? So if we take the rule and split it out like that and solve for this jk thing, it actually shows you how you can get if we don't start at 1, because that's the big question. What if we don't start at 1? Well, if we don't start at 1, like right here, so the whole reason to teach you this is to show you what to do at 1. It also shows you some other consequences that happen in calculus, so they'll draw upon it when needed. But if you had to just sum from 5 to 18, well, we don't have any formulas that start at 5. It's got to be the sum of the first 18. So what we do is we go big. We go the first 18 terms, right? So can you picture that? You got the first 18 terms. Let's see what they look like. 1, it's a plus, right? 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way out to 18. And what they're saying is, let's remember what we want. Let me put in red what we want. We want the sum from just 5 to 18. So we want this sum. So what are we going to do? We're going to go get, with this guy, the big sum and realize that it's way too much. What are we going to take out? We're going to take out this part right here, the first 4 terms. And so we use the formula to justify that, oh, let's take a look at the sum of the first 18 terms. Well, we know what that's going to be. Let's do that really quick just for extra practice. It's going to be 18 times 19 divided by 2. And then we're going to subtract from that the first 4 terms, which is going to be 4 times 5 divided by 2. And so we're going to get 10 out of this one, and we're going to get whatever 9 times 19 is. 9 times 9 is 81. 9 plus 8 is 17. And so we're going to get a 171 minus 10 is 161 is the sum. Now let me show you the pieces. The 10, you can see easily right there. That's what we took out. The 171 was all of this, but the 10 was 4, 5, 6, 7, 8, 9, 10. Those 10, not that sum of 10 that wasn't part of the original ask right there. And so very simple, very I shouldn't say simple, very logical in that sense. And so you can watch him do it here, right? So the sum of 3 to 8. So we're going to go 1 to 8 and then just subtract out those first 2 terms. We don't go 1 to 3 because we want that third term. We want the third term, fourth term, fifth term, sixth term, seventh term, and eighth term. What we don't want when we go from 1 to 8 is 1 and 2. And so we're getting rid of that. Where is that being gotten rid of? Right here. That's the sum of the first 2 terms coming through. And then example 2 starts at 4, goes to 7. So he goes 1 to 7 and then subtracts out 1 to 3. Pretty nice. So these are famous series. Now, Mclaren series is a very heavy calculus term. That's what you're going to be doing in Calc 2, is getting a Mclaren series so that you can integrate and do other things to some pretty crazy what they call non-transcendental functions like e to the x. That function, right, that sequence right there represents e to the x. If you ran that, you would get e to the x if you sum from 0 to infinity. It would limit out at e. This would give you sine x for all x, right? You want sine of 30 degrees, put 30 degrees in there and go, right? I think, actually, I apologize, I should state in radians. Degrees aren't real numbers, so it'll probably fall all apart if I use degrees. But look at these common functions that you're going to get Mclaren series for. So you're going to have to deal with series. You're not going to have anything this heavy right now, but we want you to understand that there is some heaviness coming, but what we want is a solid foundation so that you understand notation and how to work through some things.